Okay. So we're starting today's class now, which will be on elastic scattering as a classical oscillator, or specifically a classical driven weakly damped. Okay? So you remember last week we already drew this little picture where we had an incoming electromagnetic wave now of some certain frequency, and that then interacts with an oscillating electron. I'm going to put it to be an electron today. Okay? First, today also, because we're dealing with oscillations, we're sometimes going to use the angular frequency. As you know, the angular frequency and the, shall we call it the regular frequency, which we normally use when we discuss here, are just related by a factor of 2 pi. Yeah? It's just that it's convenient for the mathematical expressions to here work with the omegas, the angular frequencies instead, sometimes. And then our objective was to figure out what the cross-section in this expression was, where we could express this as essentially the decrease in the incoming flux and the relationship between the power emitted by the electron. And for these, we already got the expressions, right? The incoming flux averaged now, that's why I put that, is just C over 8 pi E0 squared, where E0 is the amplitude of the electric field, the incoming wave. The power was 2/3, but we took the average, and then we know that came out as 1 half, so 1/3. Then it's then the charge squared divided by c cubed, and then we had the acceleration squared. So this was Larmour's formula, and this was the Poynting flux. We go back to our previous class if we have forgotten them. All right? Now, clearly then, okay, in order now to figure out what the cross-section is, well, we need the acceleration, the response of the electron to this interaction. So what do? All right, well, we're sort of working classically now, right? So what do we do in our classical physics? We set up Newton 2. Sum over forces, we're going to put it in the c direction now, so in the z direction directly, equals to the mass times the acceleration, which I today will write as dot dot. So this is just the 2c, the t2. It's just a way of writing the second time derivative. Familiar to you from calculus and your mechanics A. So what forces do we have? Well, we have the driving force, right? The driving force is the incoming electromagnetic ray, so that's the Lorentz force. We knew that the Lorentz force for a charged electron was just E plus V cross B divided by C. We're always here in the non-relativistic limits. This is just little e times the electric field E. Little e is the electron charge Now, we're going to write this. It's an incoming wave. So it's E omega t. Okay? Where omega here is the frequency of the incoming wave. And this now really, I see how pedagogical it is, because this is the exponential, of course, and this is the electron charge. We should have kept the Q. Why didn't we keep the Q? Anyway, it's clear from the context. You should know that anyway. That was funny. Anyways, what more do we have? Well, we have the restoring force. That's our standard in our oscillating system, which we're going to write as this now, storing in the C, as minus the mass times omega 0 squared, where omega 0 now is the eigenfrequency of the oscillating system, again, as is familiar to us from our Mechanics 101, our Mechanics A course. And then also, we're going to have to deal with a damping force. Now, that damping force, we're going to write as minus m gamma. Here, I forgot the C, of course, in there. Should have pointed that out. And we're going to take that to be proportional to the velocity. Now, in oscillating systems, such damping forces are probably familiar for you from before. For example, friction, you know. If you push somebody on the swing, you get friction from the air. That's why you don't go infinitely large, and so forth. Now here, the friction comes, well, the damping force, not friction, comes from the fact that the electron is radiating, that is, it's losing energy. All right? So that's the connection here. Yes? Yes. The exponential I omega t. I is the complex way of writing this. I write it in the complex way. We could write it with cosine of sine, but the solution then is so messy. It's much, much easier when you use the complex numbers. And actually, we're going to do it even simpler than that, you know. But we could also just express this in cosine and sines, of course. Yeah. Now, let's set this up. What do we have? Assuming that we didn't do too many errors, well, we have the charge right, and then E0, and then we have our driving force here, I omega t. We have minus m omega squared c, and then we have minus m gamma, the velocity equals to m v dot dot. I forgot to say that gamma is our damping coefficient. All right. Now, indeed, this equation we recognize as the expression for a classical oscillator that is driven and damped. Take away this term, you get the harmonic. Yeah, that's where the eigenfrequency here comes from when you just replace this by your spring constant k, right? Now, here's your damping term, and here's your driving force. Okay? So what we're going to see is that we can analyze this system completely, in principle, analogous to how we analyze this in our classical mechanics course. Right? So, we can just write down the solution because we have done it before. If you don't remember it, you go back to your classical mechanics course. I brought the book I had as an undergraduate. I will show it to you later, because there were some nice references to this specific system in it, actually. Okay? We'll come back to that when we discuss some properties. But now we will write down the solution. There's no point for us today. We want to get to the point that is relevant for us here today. So the trial solution is of that form. And of course, one thing that we will is that if you take the time derivative of this 2 times, then we know that what comes back is just this e I to the omega t equals minus omega squared c, right? That's actually something we will use later today. And we also have that we can solve for the amplitude. We know I have to actually look up the expressions here now because I don't really remember them. Times 1 divided by omega squared minus omega squared plus I gamma omega. Okay? Now we take the complex conjugate of that to get to our absolute value of, that is the real part of our acceleration squared. And then that is just e squared, e0 squared divided by m squared omega 4 omega 2 minus omega 0 and then squared plus our damping coefficient here omega squared. Okay, so what do we see here? Well, this is nice because here is our acceleration for the system. So what we can do then is, I'm going to take this away now. We can just use this expression and write down the corresponding expression. We could do it directly for the power and analyze the power. But what we have, since we're interested in the interaction coefficients for our radiated transfer language, we wanted the cross-section, right? So we had that our cross-section was just the average value of the power by the average value of the Poynting vector flux. So we can write that down. I have to look back in what I had, right? So here we had 1/3 e squared divided by c cubed, and then we have the acceleration squared, so we just replace it. 4 divided by plus. Okay. We have to divide this by the Poynting vector, which was c 8p e0 squared. Okay. So what we can see here is we can simplify a bit. The amplitude vanishes. We have some E4s upstairs. I'm going to have an E4 upstairs there, right? We're going to get an C4 downstairs. We have an M2, which is here the mass of the electron. So I'm going to put the mass of the electron squared, right? and then 8 pi divided by 3. And then I have this thing here, which contains the frequency dependence, and that's this one, okay? Okay, so this is interesting, because in front here we have a constant. So what we can do is that we can write this as omega, that the cross-section at the given frequency is a constant, and I'm going to call that sigma Thomson, or TH. And then we have a function here, which is essentially a function there of omega, omega 0, and gamma. So gamma being the damping coefficient, this is the eigenfrequency, the system, and this is the driving frequency, the incoming wave frequency. This constant here is 8 pi divided by 3 E4 C4 ME squared, which sometimes you will see as 8 pi divided by 3 times the classical electron radius squared. It's called the classical electron radius because before we knew so much about the atomic structure from quantum mechanics, this was sort of an estimate. You can see that this has the units of cross-section, right? So this has the units of radius squared. And this was an estimate of the size of the electron. It's not correct, though, so to speak. But that's the terminology often used, so I will just give you that. It is a constant, and it is 6.65 times 10 to the minus 25 centimeters per squared. That constant is very important for our astrophysical applications, though. This is the Thomson cross-section. It is a constant, and it's very important as an opacity source in many astrophysical applications, perhaps most prominently for the universe itself before the so-called era of recombination. We will come back to that many times. All right. There we had that, and perhaps I will also just repeat, so we have it here, that the function which contains here the frequency dependent is this one. Right. Since for the majority of the course we use ordinary frequency space, right? We can just write it down also in corresponding frequency space where it has this expression. The constant, of course, remains the same. That doesn't have any frequency dependence in it. And then it's just nu squared minus nu 0 squared plus gamma divided by 2 pi nu squared. That is in ordinary frequency space, okay? The same expression. So what we're going to concern ourselves with from now on is 3 different limits of this formula here, okay? Of this interaction here, of this classically driven damped oscillator, the atomic oscillator. And those are the Thomson limit, the Rayleigh limit, and the resonance limit. Now, the Thomson limit is, as we will see, very important for free electron scattering. Okay? As applications, you will, during the course, see it both, as I said, as the basic opacity source in the universe prior to the era of recombination. You will also see it in one of the exercises that we will do when we discuss the Eddington upper mass limit of stars. That's 2. The Rayleigh scattering is important in the sense that here's our explanation why the sky is blue. So that's always nice when you talk to your friends to be able to explain, of course. Now, the resonance case here is where we get a first feeling for a spectral line, a resonance spectral line. Now here it comes with a caveat, of course, that this is in the classical limit. Nonetheless, we can, even with that limitation, say, we can learn quite a lot about the basic features of particularly why spectral lines are so prominent as they are. Then we will have to modify this part with quantum mechanical behavior, of course. But we will discuss that. So we will understand where it comes from. I don't know what we want to start with. Let's start with the first, the Thomson limit. Well, hopefully now you have already figured out what the Thomson limit is about. Yeah? We call the certain cross-section Thomson cross-section, so hopefully we get to use that. Yeah? Now, this limit is when the incoming frequency, the driving frequency, is much, much larger, greater than the resonance frequency. Okay? So we're going to look at our basic formula here. Let's see this one. Yeah? Our incoming frequency is much, much greater than the resonant frequency, the eigenfrequency, nu 0. And then we're going to have to do an a priori assumption here, which turns out to be very true, but we haven't shown it yet. And that is that we have weak damping. We don't have strong damping systems. Then we actually don't get. If we have too strong damping, we don't get an oscillation in the first place. But in this case, we assume weak damping. That is that the damping coefficient is much, much smaller than our gamma. So if we do that, then, okay, this one is much, much greater than this one. This vanishes. This one essentially goes to 0 in comparison today. So this one also vanishes. And we're left with, well, sigma Thomson, nu to the 4th power divided by nu squared squared. So that's nu to the 4th power. So in this limit, it goes to, indeed, the Thomson cross-section. And that's a constant. So 2 things here that we want to say about the Thomson cross-section. That first you can say, okay, what in the limit that we don't have any eigenfrequency, so that is that. We don't have any damping, so that's 0. Well, that's the response of a free electron. So that's why Thomson scattering is used to describe the scattering of free electrons as well, right? And this is why actually it's free electron scattering that is the important Thomson part for a lot of astrophysical applications, like those that I mentioned, scattering prior to the era of recombination, inside stars where it's very hot. So a lot of the gas is ionized. We have a lot of free electrons around. Then Thomson scattering is important. In general, that's actually true that when you have a lot of free electrons around, that is the gas is ionized, then Thomson scattering is an important opacity source. When you don't have a lot of free electrons around, it is, of course, not. One more thing about Thomson scattering, and that is that when we have the situation that the incoming frequency here is very high, that is, the energy of the incoming photon is very high, we're going to have to modify this result. Because then we cannot assume that, like the title of today's lecture say, that scattering is elastic. Scattering here, elastic means that the incoming frequency is equal to the frequency of the scattered frequency. The energy doesn't change. And that's the case in Thomson scattering, free electron scattering, that nu is nu incoming in the scattering process. Here, we scatter off there, is equal to, if this is then the incoming frequency and this is the out, they're the same. So there is no energy change there. But if this is too big, that's not true. We can actually kick the electron a little bit. So we're going to have to modify this to take that into account. That's called then Compton scattering. And that's the general case for the Thomson. So Thomson is actually, so to say, the low energy limit of the general Compton scattering case. All right, next. Let's, well, okay, so we took this limit. Let's take the opposite then. That's, the easiest way, right? That's called the Rayleigh scattering limit. So that's when, again, nu, much, much smaller than nu, and again, we're going to take the case that the damping is weak, okay? So if we take the case that the damping is weak, and we can, so to say, neglect this term then we can see that to a first approximation, this vanishes, and we're only left with this one, okay? So in the opposite here, you see that this is then approximately the Thomson, and then you have nu divided by nu 0 to the 4th power, which you can also, and you often see this expressed as the opposite, so you can take the wavelength instead, then you have the resonant wavelength on top here, and this one at the bottom. And that's an approximation then for the Rayleigh scattering cross-section. The Thomson cross-section is a constant, so that's an exact expression as long as we don't go into the Compton regime. This is only a crude approximation for the cross-section. All right. Let's see. We want to discuss some case of the Rayleigh scattering, which might be interesting. And I actually hinted toward it already. I'm going to write it up here so we can use that part as well. This is the Rayleigh scattering regime. We have that nu much, much smaller than nu 0, or lambda 0, that is the resonant wavelength, is much, much greater than no. Now I have it opposite, yeah. There is a typo here. I'm glad that somebody figured it out, right? Because we took the same limit as before. This has to be the opposite, right? Yes. This one is correct. The other one was, of course, not correct. Sorry. Right? This one has to be much, much greater than lambda 0 because it's the inverse. Very good observation. Very good observation. All right. Let's continue then. Once we have that sorted out. And we know that the cross-section now is approximately then Thomson, and then times lambda 0 divided by lambda to the 4th power, right? So you can see that this has a very strong wavelength dependence, 1 over lambda 4. Resonant wavelength is, of course, constant. All right, so let's take our example now. We have some sort of cloud here, yeah? Atmosphere, say, and then we have an illuminating source somewhere. Let's place it here. I'm going to place this one here. I'm going to place some illuminating source here. And that illuminating source now is going to shine with some sort of, we can approximate it as a black body with a temperature, say, of 5,800 Kelvin. And then we know from Wien's law that the maximum wavelength, okay, it has a distribution, but the maximum wavelength is on the order of 5,000 angstrom. That's where it emits most of its light, approximately now, okay? So let's say that this is a neutral hydrogen cloud. And then we're going to have to figure out, and for this specific example, we need some knowledge either from the experiment or from next chapter in our course. So we're going to say that, I'm going to give you that now, that for neutral hydrogen atoms, if you want the first transition, you can call it, from these two states, okay? Then that has a resonant wavelength. We will learn this, how to calculate it, don't worry. 1216 angstrom, okay? That's the resonant wavelength. So clearly, you can see that in this case, lambda that comes in is much, much greater than the resonant wavelength of this hydrogen cloud. Right? So we're in the Rayleigh regime here. Okay? So then we can say that, yeah, we have some... Oh my God, this was a mess. Lambda 0, 1216 angstrom. We can place a little observer here, and we're going to look at that cloud or that part of a sky up here, okay? And then we know that the particles here, they're going to scatter the light that comes from this source over here, and they're going to use Rayleigh scattering to do so, and some of those are going to be scattered into this person's receiver, which could be like eyes, could also be a telescope or whatnot. And then can say, okay, what will this person now actually see? Well, we know that Rayleigh scattering is more efficient the shorter the wavelength, right? Now, the peak wavelength here is at 5,000 angstrom. But since this is a black body, we know that it doesn't only emit at 5,000 angstrom, right? We had something from our earlier in the course that emits a little bit there, and then it goes up, and then it goes down again, okay? This is not at all a representative because we had the exponential cutoff, remember? And then we had the power law, but this is just an illustration. The peak was here, right? But also at shorter wavelengths, we do emit some, of course. Now, the thing is that, of course, then, will be scattered more efficiently. So depending on the receptor, how sensitive this, the tuning of the eyes, of course, in this case is, we might actually see some peak wavelengths that are different than 5,000 angstrom. Yeah? So now if we say that, okay, but this is, of course, our eyes, where do we see? What is the shortest wavelength that we see? Well, it's basically blue. The shorter wavelengths we don't see. And of course, then somebody who's very astute can say, actually, we see violet as well. A little bit there. But then, yeah, you have to do the folding. Because if this peaks at 500, say in the green, in the yellow, and we see all the way to the violet, but of course, there is a little bit too little violet radiation to come to us, actually, to make that. So you have to fold with our perception, our receptors, our transmission, with the amount of radiation actually comes. And that then turns out to peak in the blue. And yeah, this is why the sky is blue, of course. Again, with the caveat for the details that I said, and also, of course, well, you know, our atmosphere is not really composed of hydrogen, right? It's various molecules up in the air that we have. There's actually the scatterers here. But it works the same way. It's just that we will learn how to calculate the resonant wavelength for hydrogen. So I took that as an example. Okay? So yeah, that was great. And now we can tell our friends in the evening why the sky is blue. We'll take a break, and after the break we will move on to the next, which is then line scattering.